In our last video, we're going to take a look at how to find that plus c. What does that variable represent? So what we've actually been finding when we write, say if I look at this last example here, 6x to the 4/3 minus 12x to the 1/2 plus c, we actually have found what's called a family of antiderivatives, because this plus c, that c could take on any value. There's infinitely many solutions. And if you were to look at the graph, if you were to graph a bunch of them and say, okay, plus 1, plus 10, minus 2, what you would see is you would see the same graph just translated up and down, just kind of moved up and down, and that is the family of antiderivatives. There's infinitely many of them. But as soon as you give me a single point on that graph, it locks it into one single particular antiderivative. So if you tell me one point that's on my graph, I can then find exactly which antiderivative we're talking about, which member of the family of antiderivatives that we're talking about. So here, or start off, I have f prime of x equals x to the minus 1 minus 2x to the negative 2 plus 1, and I'm given the initial condition f of 1 is equal to 5. So I want to, I'm starting with the derivative, I'm trying to work my way backwards to f of x. So I need to start by taking the antiderivative, or taking the indefinite integral. So I would like to integrate x to the minus 1 minus 2x to the minus 2 plus 1. And this is nice. They even wrote it with negative exponents. I don't have to worry with that stuff. Here with this guy, x to the minus 1, add 1 to the power, x to the 0, divided by my, oh, shoot, they got me. X to the 0 over 0 can't divide by a 0. Keep an eye out for x to the minus 1. It's something that will sneak in every now and then. X to the minus 1, really just another way to write 1 over x. And then as soon as we write it that way, we say, oh, okay, you must mean the antiderivative of this guy is natural log of x. So when I take my indefinite integral of 1 over x, I'll have natural log of absolute value of x minus, okay, let's continue on here. 2x add 1 to the power should now be negative 1 divided by my new power of negative 1, plus this constant of 1 is just going to pick up a factor of x, so plus 1x plus c. So I'm just going to clean this up a little bit, make it easier to work with. Minus a negative is plus a positive. I'm going to rewrite this negative exponent here. This is really natural log of absolute value of x plus 2 over x plus c. So I started with the derivative, found my antiderivative, and okay, here is f of x currently. So this is my kind of, in air quotes, original function. This is f of x rather than f prime of x. And normally I'd say, well, there's my answer, let's move on. But now I have this other point. They tell me f of 1 is equal to 5, which gives me a way to solve for c. So I'm going to, off to the side over here, I'm going to say, well, what does f of 1 really mean? This says I'm taking 1 and plugging it in for x. So I'm going to take 1 and plug it into x into this equation right here. So f of 1, this is natural log absolute value of 1, plus 2 over 1, plus 1, plus c. I don't know what c is, so I just have to leave it as plus c. And f of 1, we said that was equal to 5. So all of this equal to 5. So what I really have here, if I look at just this piece, is I have this equation that I can solve for c with. So natural log of 1, that's 0, plus 2, plus 1 plus c is equal to 5. 3 plus c equals 5, which means that c is equal to 2. I'm almost done. The last thing I need to do then, so I know that for this particular antiderivative, c is equal to 2. I'm going to take that and plug that back into my f of x here. So my solution to this problem is f of x equals natural log absolute value of x plus 2 over x plus c, but we just said, hey, c is 2 for this particular antiderivative, and here is my solution. So most of the problem is what we've been doing up until this point. We just have a little bit of algebra to do here at the end. That's really the only difference, is we have a couple little bit of algebra steps at the end. Here in this case, we've got another example. We're using a slightly different notation this time. We have dy over dt equals 3 minus 2e to the t, and we're told that y of 0 is equal to 8. So here in this case, this one's a little bit tricky. You can sort of think about this as multiplying both sides by dt. That's not really what we're doing. But that allows you to set up this equation where we say, okay, I'm going to integrate dy is equal to the integral of 3 minus 2e to the t dt. Because this is really just another way to say, hey, this is the derivative with respect to t. So if I integrate dy, that's really just 1 dy. Again, I'm integrating here with respect to y. So this would be y equals, on the right-hand side, well, first I integrate 3. That's just a constant, so that's going to pick up a factor of t, so 3t. Antiderivative of negative 2e to the t. Well, I know that that's just going to be negative 2e to the t power. Right? Again, if you're unsure, take your derivative. Check your answer. Derivative of negative 2e to the t, that is, yes, negative 2e to the t. And then, of course, plus my constant of integration, c. But we're given this condition right here. We're told that y of 0 is equal to 8. So I'm going to, let me do this in a different color over here. And we'll do it in red. So I'm told that y of 0, this just means I'm going to plug 0 in for t, is equal to 3 times 0 minus 2e to the 0 power plus c. This is all equal to 8. So I'm going to solve this equation for c. So I have 0 minus 2 times 1 plus c is equal to 8. So this is negative 2 plus c equals 8. C must be 10. So for my solution then, for my particular antiderivative, I just want to take this c equals 10 and plug it into my equation for c. So y equals 3t minus 2e to the t plus c, but we just said c is 10. So here is our particular antiderivative. So this is really, really neat. These are actually very simple examples of something called a differential equation. And there's a whole branch of mathematics devoted actually just to solving differential equations. It turns out they're very, very useful and very, very practical. If you're interested in it, Moraine Valley actually has a differential equations course. So if you wanted to, you could just study differential equations. And of course, they're going to get a lot more complicated than this, but just know that it's actually a huge field of study within the realm of mathematics. Let's look at one more example. Here I have the marginal cost of producing x units of a commodity is given by c prime of x is equal to 0.3x squared plus 2x, and the fixed cost is $2,000. We would like to find the cost function c of x and the cost of producing 20 units. So here we're bringing back some ideas from chapter 2 way long ago. We have this idea of marginal cost right here. Marginal cost, remember, that's just the derivative of our cost function. We don't need to overcomplicate this. So I'm starting with c prime of x is equal to 0.3x squared plus 2x. I want to take this somehow and find c of x is equal to blah, and then the cost of producing 20 units. Once I have c of x, that'll be easy enough. I'll just plug 20 in for x. So I have the derivative. I want to work my way back to the original function. Sounds like a job for indefinite integrals. So I'm going to integrate 0.3x squared plus 2x with respect to x. If you want to, on the other side, you can say, well, we're integrating c prime of x dx. And when I integrate that, I'm going to come up with a c of x. And I think that might be helpful just in remembering what we're dealing with, or if we're dealing with the derivative or the antiderivative or the function. So here I'm going to integrate each of these two terms, just a power rule for each of them. So I'm going to add 1 to the power. I should have x to the third divided by my new power of 3. That'll give me 0.1x to the third. Plus over here, add 1 to the power x squared divided by 2. That'll cancel my 2's. And then, of course, plus my constant of integration c. Here in this case, I'm going to choose a different letter just because we already have c of x, and I don't want to get confused by it. So I'm going to say, how about d? I just need some constant over there. So now, I'd really like to know, well, what is my cost function? Well, this is a cost function. It's actually infinitely many cost functions because I don't know what d is. I don't know what that constant of integration is. So I would like to find that point. Only the problem is we don't have an ordered pair like we did in the last couple of examples. We don't have, they don't outright tell us, hey, c of blank is equal to blank, right? We don't have that piece of information. Well, actually, we kind of do. It says, particularly right here, the fixed cost is $2,000. So when I say the fixed cost is $2,000, really another way for me to say that is no matter what, I have to pay a cost of $2,000. In particular, I have to pay a cost if I manufacture 0 units. That will still be $2,000. So whenever you see something about fixed cost, that's really what this is trying to say. It's trying to say c of 0 equals 2,000. No matter how many units I produce, including 0, I have to pay at least $2,000 in costs. So this gives me a way that I can solve for d with. I can say, well, c of 0, that's equal to 0.1 times 0 to the third plus 0 squared, plus I don't know what d is, so I'm going to leave that there. And all of this is equal to, we said, 2,000. So I have 0 plus d is equal to 2,000. So d equals 2,000. So that means my cost function, c of x, is equal to 0.1 x to the third plus x squared plus d, we just found that as 2,000. So there is my cost function. Here's the first part of my answer. So find the cost function. We just did that. The other piece it wants, it says, and the cost of producing 20 units. This one is relatively straightforward. You're just going to evaluate this at x equals 20. So you're going to look at, well, what is c of 20? 0.1 times 20 to the third plus 20 squared plus 2,000, and you would go and calculate that. I'll leave that as an exercise for you to do. One thing I'll mention about this problem, a really bad habit I'll see some students use is they'll say, hey, if I see c of 0 equals 2,000, I feel like that gives me a free pass to just conclude that my constant of integration is equal to 2,000. Please don't make that mistake. It's a very, very easy mistake to make. Look back at our last example. Here we said y of 0 is equal to 8. Notice that our constant of integration was not 8. It was 10. So we want to be careful. You do need to go and actually plug in 0 for x and set your function equal to 2000 to solve for that variable. Otherwise, it's going to be really, really easy to make a mistake when you are solving for that constant of integration.